Hello everyone. In this video, we'll start discussing about constraint optimization. And here comes the list of topics. First, let us see introduction to constraint optimization. Then we'll talk about penalty and barrier method. In that, we'll be using some penalty functions and barrier functions to convert the constraint optimization into unconstrained optimization. Similarly, there are Lagrangian methods available, augmented Lagrangian method. In that, Lagrangian functions are used to convert the constraint optimization into unconstrained optimization. Apart from this, there is something called polynomial time algorithm for linear programming. It is available. Then direct use of successive linear programs with two different cases, linear constraint case and the general nonlinear programming cases are available. So the first, these two topics we'll see in this video. Next, augmented Lagrangian method and polynomial time series linear programming algorithm we'll see in the second video, and finally we'll see the successive linear program, the last. So first we'll start with constraint optimization. So before getting to constraint optimization, what is feasible design, infeasible design, and optimum design that we should know? What is feasible design? If the design that satisfies all the constraints means that particular design will be called as feasible design. In case a design that violates one or more constraints, then it is called as infeasible design. Because of optimum design, it is going to be choice of variable out of n number of design variables. We do take a particular variable, or we do give a limit to the variable from this range to this range, this particular variable, and that does the minimization or maximization of objective function. At the same time, it satisfies all the constraints. That we call as an optimum design. So the choice of design variable that minimizes the objective function while satisfying all the constraints is called optimum design. So that's based on that only we're going to define what is optimum design means. In general, converting the constraint optimization algorithm into unconstrained optimization is called design optimization. Okay, so there are many methods available, especially three methods are very famous. The first method is called indirect method, where they will be transforming the constraint optimization into unconstrained optimization problem. And there is another one is multipliers are used, like our functions are used. What is the function? Penalty function or augmented Lagrangian multipliers are used in that second method. And third method, it's called direct method. Maybe sequential linear programming approach is used, or SQP is used, or steepest generalized reduction gradient methods, GR used. There are many methods available. We'll be focusing on some penalty functions and augmented Lagrangian multiplier program. Then some linear programming concepts, sequential linear, successive linear programming concepts we will be discussing. And time series linear programming concepts also will be touching on. So that's about the optimum design. Keep in mind that optimum design is nothing but with respect to constraint optimization is nothing but converting the constraint optimization into unconstrained optimization by using any one of these three methods: indirect approach, penalty function or augmented Lagrangian multiplier, or finally direct method. Fine. With this introduction, let us see what is first of all constraint optimization. We know the mathematical formation of optimization problem: minimization of f of x subject to gi, where it is less than or equal to bi, where I varies from 1 to m. In this case, f belongs to the set R, n, where n is the dimension and x is the design variable over here, which are unknown of the problem. They must be linearly independent. And g belongs to Rn, and it is inequality constraint. So this cases, if you see, this is the objective function, and this is your f naught is your function, x is the independent variable, and over here this is your constraint and the constraint function. So it is inequality. There is inequality constraint, equality or inequality. This is the constraint we have. If it is equal to 0, then it is not a problem. If it is equal to equal to some number. So the constraint exists over there. So then it is called constraint problem. Okay, so constraint problem. So an optimization algorithm with respect to constraint problem may be a large scale problem or a medium scale problem. When it is a large scale problem, it uses linear algebra that does not need to store or nor operate on full matrices. But in contrast, if you see the medium scale method means it is internally generate full matrices and uses dense linear algebra. So that's the basic difference between this large scale and medium scale constraint optimization. Okay, and the definition is actually based on KKT conditions. It is very similar to your gradient approach. A little modification is being used over here. Let us see what is the gradient approach. What we do, the derivative should be equal to 0 at the minimum point. Same way here also we're going to consider your KKT conditions. So the difference is that the KKT condition holds for constrained problem. That's the only difference. There is gradient is for your different approach and maybe unconstrained problems. But KKT conditions are for constrained problems. Okay, so KKT conditions uses the Lagrangian auxiliary Lagrangian function. So that can be written like this: your main function plus auxiliary functions, and the auxiliary functions gi is your maybe inequality constraint and h is the equality constraint. These constraints, inequality constraint and equality constraints, are multiplied by the respective Lagrangian multiplier called lambda g and lambda h, and all this the summation of all this product as well as summation of this product has been added to the objective function, and that forms a new function called L of x comma lambda. L of x comma lambda, where here the lambda, the vector lambda is concatenation of lambda g and lambda h. Lambda g and lambda g h are nothing but Lagrangian multiplier. So now what is the condition? If you look into it, the derivative of this function what we have made, that is the L of x comma lambda with respect to x, the derivative of this, the del x of L of x comma lambda should be equal to 0, and so we know the h is the equality constraint, equal to 0 constraint, and this is not equal to 0 constraint. So the not equal to 0 constraint, we are using a multiplier lambda g. So when you multiply the lambda g with the g, it should end up in 0. That is one constraint. Then another one is the entire function when you take derivative, that should be equal to 0. So these two are the important conditions. Okay, apart from this, what you should remember is, as I told you already, the lambda g should be greater than or equal to 0, and the h of x is equal to 0 constraint. G of x is maybe here in this case less than or equal to 0 constraint has been used. So that is about the constraints on the details of the constrained optimization. So here again the constraint optimization can be classified like with respect to the design. It may be a behavior constraints or it may be side constraint. What is behavior constraint? The constraint that represents the limitation on the behavior or performance of the systems are termed as a behavior or functional constraints. And what is the side constraints? So the side constraints are nothing but that represent the physical limitation on the design variables such as manufacturing limitations. So that's why I said like x can vary from x1 to x10. Means that is a physical limitation. The design variable is only ranges from x1 to x2, means it is a side constraint. Whereas if there is a performance constraint, that is the output function f of x, as can vary from only from this to this, means it's a functional constraint or a behavioral constraint. So anything based on design variable is a side constraint. Anything based on the function is called a behavior constraint. That's it. That's simple it is. And the next is next kind of constraints are linear and non-linear constraints. Already you know about linear non-linear constraints. It is very simple again. So linear constraints are nothing but the constraints will have only x terms in it mostly. Or non-linear constraints, when you say, those constraints will have x squares terms in it. So again, in the case of linear constraint, it starts from initial feasible points, then all subsequent iterations are feasible. It lies in the feasible region itself, and can construct such direction and step length so that the constraints are satisfied. The improvement are from x of k to x of k plus 1 based on the objective function j of k in the case of linear constraint. This is what we have learned in during our first half of the course. And the nonlinear constraint, it is not very straightforward to generate a sequence of feasible iterations. But if feasibility is not maintained, then need to decide whether xk plus 1 is better than xk or not. We have to decide. So based on the decision, we move on in the case of nonlinear constraints. Apart from this, as we know already, we discussed the constraints again, maybe inequality constraint, equality constraint. Like that, we can decide based on the symbol used, that is whether it is equal or not equal, inequality. Okay, that's another classification we have with respect to constraints. Now, a small example for constraint optimization. This is the function given where it is called a parabola, that is x minus 2. Since it's little shifted up, it's going to be x minus 2 whole square plus 1 is my function f of x. Okay, for this, two constraints are, one constraint, another one is boundary. Here the constraint c of x is less than or equal to square root of x minus 1. That means this is the constraint I have. This is the constraint. The another one is bound, that is x is greater than or equal to 0. That means this area greater than or equal to 0, this area, and this one, and square root of x minus 1 is constraint area should be less than in this. So that means over here it is down and over here it is up, and extra this areas. So that's the constraint. So you can see that very well here. And this is the region. This is the region we are talking about. So for this curve, for the constraint curve, what we have, okay, what we have. So when it is positive, x is positive. This is the curve. X is positive, it is below. When x is negative, when the constraint is negative, it is the above area. So this area, and then boundary is x greater than or equal to 0. That means what I'm trying to say is, I just highlight it, and so that you can understand. So this is below this curve, this much, and over here this much. Okay, this much. For this is for the constraint. For the bound, what does bound mean here? The bound says this is the boundary we have, bound. Okay, so all this which comes this side is the bound. So when you when the constraint and the bound, when you combine together, your feasible region will be, I use another color so that we can understand. The feasible region is red, and I'll use it. The feasible region going to be this much. This is your feasible region. This is your feasible region. That's what it says. The x is from 0 to 1. And the rest all, that x greater than 1, the x greater than 1 is infeasible region. And with respect to this, you can just say, just substitute x over here and then compare and then say, so this is the region we are interested. And all condition has to be satisfied. When it satisfies, both kind of conditions are satisfying or not. And details we'll be dealing for this particular example throughout this, at least for your barrier and penalty function discussion, we'll be using this. Okay, and next let us see about what is penalty and barrier methods. And the basic idea already we know is nothing but convert the constraint optimization into unconstrained optimization. And while converting, how we are converting this matters, and convert to one or more unconstrained optimization problems. So the unconstrained problems are not a single optimization problem, it may be a multiple. Converting the constraint optimization problem into a multiple unconstrained optimization problem varies from single unconstrained optimization problem to multiple unconstrained optimization problem. Under function only your penalty function and barrier function comes. And the next one is called method of Lagrangian multiplier, that also lined up. In the next video we'll be discussing about it. Its objective is not reduced, and at the same time all the constraints are satisfied. Then it is called function. The metric function is given by f of j of x comma g of x comma h of x. J of x is your objective function, and the g of x is your inequality constraint, and h of x is your equality constraint. Okay, so now function, again two kind of functions available. One is called penalty function method, the other one is called barrier function method. In penalty, again there are two, interior penalty and exterior penalty methods are available. What this exterior penalty method does is, we may be appending a penalty for violating the constraints. We just going to check if there are violations, that we try to compensate. That we call it as exterior penalty method. Okay, so if there are violation, the violation is compensated. Okay, because of these unconstrained, because of this constraints, that is inequality constraint and equality constraint. Because of these two constraints, if there any parameter violating, any parameter is violating the constraint, then to compensate that, we will be appending a function, and that function or variable, and that we call it as appended penalty for exterior penalty method. And next one, we may append a penalty as you approach infeasibility, that is interior point method. So these are the two methods available. We'll see detail about it. And barrier also sometime we'll call it as a sub function of penalty, discussed in the later slides. So general approach, whether it is penalty or barrier method, what is the general approach? First of all, we have to minimize the objective function as a unconstrained function. Okay, it may be a minimization problem or maximization problem, not a problem, but we need to treat that function as an unconstrained function first of all, and after that we have to provide a penalty to limit the constraint violations. There may be some violation, and then magnitude of the penalty varies throughout the optimization function. So you need to this may be one approach, and sometimes it may be called a sequential unconstrained optimization technique, SUMT. These are the general approaches available. Pseudo objective function is given, that is pi of x comma rho p is equal to j of x plus rho p into p of x. So in this case, j of x is your original objective function, and p of x is the one we just going to impose as a penalty function. Okay, penalty function. In this, r of rho is nothing but it's a scalar multiplier. To determine the magnitude of the penalty function, it is used. See, the rho is nothing but it's this one is rho. Okay, this is rho. The rho is nothing but unconstrained minimization number. Penalty method approaches is useful for incorporating the constraints into derivative free and heuristic search approach. It's a very, very important. Penalty procedures are making this approaches as a derivative free and heuristic search procedures, so people feel easier. That's why they go for this type of penalty function procedures. So some more details about the penalty function methods. So pi of x comma rho rp equal to j of x into r rho into p of x. Already I told about this. So this is your objective function, and this is your j of x is the objective function, and p of x is your penalty function, and r of rho is nothing but it's a penalty parameter. It's a non-negative penalty parameter. Okay, the idea is to add penalty terms to the objective function. So we have added the penalty function to the objective function, which turns the constraint problem into an unconstrained problem. So that's the first thing. And now what is the procedure? See, now we'll be initializing the penalty parameter. Penalty parameter is nothing but r of rho. That will be initialized, and initial solution, and we'll initialize the solution Gauss, then minimize the penalized objective function. So that means the overall function has to be minimized starting from Gauss. So starting from this Gauss, it will be minimized. Then update the Gauss with the computed optimum, and if it is converged, you just stop. Otherwise, you go to step number 3 and repeat the process. This is the overall process. So what we do, there is objective function. How you deal with objective function, we try to minimize and verify whether it has reached the minimization minimum point. If not, then iteratively repeat the process till you reach the minima point or maxima point. Same way, right now what we have done, j of x is the objective function. With that, we have added a penalty function also. Now altogether what we do now, we will be minimizing the penalized objective function from the starting gas and check whether it is reaching the minima point in the presence of penalty function. That is what the basic procedure is. So penalty, when I say penalty function, there are again 4 methods available, and the methods are exterior penalty function method and the interior penalty function method. And the interior penalty function method, sometimes called as barrier function method, and the log penalty function method. Finally, it is called extended interior penalty function method. Okay, the effect of penalty function is to create a local minima of unconstrained problem near x star. That is after modification. After I add penalty function and the variable I call it as x star. So near the x star, I need to have some local minima when it is considered as an unconstrained problem. Okay, as we know already discussed, penalty functions are added as a penalty for infeasibility, whereas barrier functions are added as a term that prevents the iteratives from becoming infeasible. So it is a barrier is kind of different approach, and penalty function is the another approach altogether.